Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. First day on the IT help desk. Phone rings. My computer won't turn on. You walk over, pop the side panel off the tower, and just stare. Ribbon cables, a big green board, some metal boxes, little fans, and you have absolutely no idea where to start. That panic? It's real. And it's why the very first thing you need to master is what's inside that box. Welcome to Part 1 of the IT Fundamentals Masterclass. This is Computer Components Explained, from the motherboard to the power supply, in a way you'll actually remember. By the time this video ends, you won't freeze in front of an open PC. You'll know 3 things cold. 1. You'll identify every major component inside the case. Just point and name it. 2. You'll explain what each part does in one plain sentence, no jargon. 3. You'll understand how they talk to each other, so when something goes wrong, you can start troubleshooting instead of guessing. That's the difference between someone who knows computers and someone who works in IT. That big green board staring back at you? That's the motherboard, the central nervous system of the PC. Every other component, the CPU, the memory, the graphics card, the drives, plugs directly into it. Without it, nothing talks to anything. A user calls you furious. Word takes forever to open. You check, and it's not the network, it's the CPU gasping. The CPU, or Central Processing Unit, is the brain. It runs your operating system, your apps, every calculation. Modern desktop CPUs typically run at several gigahertz and have multiple cores. But here's the thing beginners get wrong. A higher gigahertz number doesn't always mean faster. A newer, more efficient chip with a lower clock speed can absolutely demolish an older, higher clocked one because of architectural improvements. Speed is architecture, not just clocks. So how does a CPU actually think? It's a 4-step loop. Fetch an instruction from RAM, decode what it means, execute it, and write the result back. This is called the instruction cycle. Without this loop, nothing happens. A quick but important note: never run a CPU without a heatsink. Without one, it can overheat in seconds and permanently damage the chip. Let's lock that in. Pop quiz. Hit pause and answer. What happens if you power on a CPU with no cooler attached? Now let's talk graphics. Why can't you run Cyberpunk on a cheap office laptop? Because it uses integrated graphics, the GPU built right into the CPU. It shares system memory and handles everyday tasks fine, but it's not built for heavy rendering. A dedicated GPU, like an NVIDIA RTX 3060, comes with its own video memory, cooling fan, and enough horsepower to push AAA games at high settings. But it adds cost, power draw, and heat. Choosing between integrated and dedicated depends on the job. If you're supporting a graphic design team, you'll need to know the difference. Storage is your digital filing cabinet. Old-school hard drives use spinning disks and a tiny mechanical arm. Cheap and massive, but slow. An SSD uses flash memory, no moving parts, and it's the single biggest upgrade you can give a sluggish computer. Swapping a hard drive for an SSD can cut boot times dramatically, often from painfully slow to near instant. Yet people still install Windows on spinning drives in 2025. Don't be that person. Know the difference. RAM is your computer's short-term memory. It holds everything you're working on right this second. Your open browser tabs, that unsaved Word doc, the game level loaded behind the scenes. It's super fast, but it's volatile. Cut the power and everything in RAM vanishes. The classic beginner mistake? Thinking RAM is the same as storage. Running out of RAM doesn't delete your photos. It just grinds your computer to a painful crawl. That's when you'll see the little hourglass spinning forever. The power supply unit, PSU, sits at the back of the case, quietly converting deadly wall voltage into the smooth, low-voltage DC that your components actually need. Look for an 80+ bronze certification. That means it meets an efficiency standard, wasting less electricity as heat, so it runs cooler and saves money over time. Here's the mistake that kills entire builds: buying the cheapest no-name power supply you can find. When a cheap PSU fails, it can take your motherboard or graphics card with it. Spend the extra money on a quality unit. Your career will thank you. August afternoon, 40 degrees Celsius outside. Your gaming PC shuts down in the middle of a match. You pop the side panel and a wave of heat hits your face. That's thermal throttling. The CPU or GPU sensed dangerous temperatures and slashed its clock speed and power to protect itself. Performance tanks. But the system stays alive. That's why cooling is never optional. With air cooling, a chunk of finned metal and a fan do the job. Cheap, simple, no pump to fail. Liquid cooling replaces that with a water block, pump, and radiator. Quieter, dumps heat more efficiently. But if the pump dies, your CPU can overheat dangerously fast. Whichever you choose, one detail will wreck your day: the plastic peel on the bottom of the cooler. Always remove it. And thermal paste? A grain of rice right in the center. No more, no less, before you clamp the cooler down. A case is not just a box you pick because it has RGB fans. The form factor of the case dictates which motherboard even fits. An ATX mid-tower accepts full-size ATX boards, while a micro ATX mini tower only accepts the smaller micro ATX and mini ITX boards. Get that wrong, and your components literally won't mount. Now, here's a real stat from the repair bench. Poor airflow is a major cause of premature hardware failure in DIY builds. A case with a mesh front and a couple of included fans can keep internal temperatures much lower than a sealed glass front box. That's the difference between a GPU that lasts for years and one that fails early. Pay attention to the front panel, not just the paint job. Peripherals live outside the case, but as an IT professional, you will support them every single day. Keyboard, mouse, monitor, webcam, headset. These are the tools your users interact with constantly. They connect through a handful of familiar ports: the rectangular USB-A, the reversible USB-C, HDMI for video, DisplayPort for higher refresh rates. And here's a call you will hear on repeat: my mouse moves, but it won't click. Before you re-image a machine, check the battery in that wireless mouse. More often than not, that's the problem. Those long slots on the motherboard are PCI Express, PCIe for short, and they are your upgrade highway. Typically, the long X16 slot connects to the graphics card. Shorter X1 slots can host Wi-Fi or sound cards, and an X4 slot may carry an NVMe adapter for extra fast storage. Always check your board's manual for exact compatibility. PCIe 4.0 can deliver much higher bandwidth than PCIe 3.0, so two generations of the same slot can perform wildly differently. Practical example: your office PC has no Bluetooth. For a few dollars, you drop a PCIe X1 Bluetooth card into a spare slot. Install the driver. And now your conference headset pairs instantly. No USB dongle, no clutter. You could name every chip inside a PC, recite the spec sheet from memory, and still be completely useless when a user says, "My computer is slow." Here's the part nobody tells you about hardware. It is not about the parts. It is about the conversation between them. When you double-click an Excel file, data doesn't sit still. It races across multiple highways inside the machine. If you only study components in isolation, you miss the one thing that actually determines whether a PC feels fast or like a slide projector. So let's trace the full journey of a double-click. The classic von Neumann architecture underpins the operation of most modern PCs. When you double-click a photo, the CPU issues a red command that travels through the chipset, the motherboard's traffic cop, to the SSD. The file gets pulled into RAM because working directly from storage would be hundreds of times too slow. The CPU decodes the image, hands the rendered pixels to the GPU over the PCIe X16 link, and the GPU pushes the final picture out to the monitor. Those pathways, the memory bus, PCIe, SATA, are the real speed limits. A cheap SSD on a slow SATA 2 cable is like driving a Ferrari on a gravel road. Understand the roads, not just the cars. The most common mistake I see on a first build. The builder pours every dollar into a flagship CPU, then buys the cheapest GPU and a single stick of slow RAM. The result? A $550 processor sitting idle most of the time while the graphics card gasps for air. A balanced spec, mid-range CPU, strong GPU, dual-channel RAM, and an NVMe drive costs the same or less and actually delivers the frame rates the unbalanced build promised. Every part runs near its limit together. No single piece drags the whole system down. That's the definition of a well-built machine. A PC's hardware profile looks completely different depending on the job it needs to do. An office machine handling email and spreadsheets runs happily on a modest processor, 8 gigs of RAM, and a small SATA SSD. A modern gaming rig jumps to a 6-core chip, 16 gigs of RAM, and a 1 terabyte NVMe drive so game levels load in the blink of an eye. A small business server might pack a multi-core processor, plenty of error-correcting ECC memory, and a high-capacity hard drive array because data integrity and capacity matter more than raw speed. No single spec sheet fits all. Match the hardware to the use case. A PC's hardware profile looks completely different depending on the job it needs to do. An office machine handling email and spreadsheets runs happily on a modest processor, 8 gigs of RAM, and a small SATA SSD. A modern gaming rig jumps to a 6-core chip, 16 gigs of RAM, and a 1 terabyte NVMe drive so game levels load in the blink of an eye. A small business server might pack a multi-core processor, plenty of error-correcting ECC memory, and a high-capacity hard drive array because data integrity and capacity matter more than raw speed. No single spec sheet fits all. Match the hardware to the use case. A traditional hard drive is the baseline. A SATA SSD is several times faster. An NVMe Gen 3 drive is dramatically faster. And the latest Gen 5 NVMe drives push speeds even further. Check current benchmarks for exact model numbers. Here is the trap that catches beginners. M.2 is just the connector shape. You can buy an M.2 drive that still speaks SATA and never exceeds SATA limit speeds. If the box says NVMe, you're getting the express lane. If it says SATA, you're stuck at a much slower pace, even though the stick looks identical. Always read the fine print. Let's lock in that storage knowledge. Quick checkpoint. DDR4 and DDR5, they look almost identical, but the notch position is different. DDR4's notch is offset, while DDR5 sits closer to the center, making them physically incompatible. No exceptions. For content creation, DDR5 can slash video export times and handle large timelines far more smoothly. If you're building a new PC now, DDR5 is the modern standard. Don't buy a DDR4 board thinking you'll upgrade later, because the slots won't accept DDR5. If a new PC powers up but won't boot, the BIOS or UEFI is your first stop. It's a low-level environment that lists every detected component. As soon as the logo appears, mash the DEL key, or F2 on some boards, before Windows loads. Once inside, the main screen shows your CPU model, installed RAM, and storage drives. If the RAM reports less than expected, one stick isn't seated. If the SSD doesn't appear, check the SATA cable or reseat that M.2 drive. No OS tools needed. This is hardware truth right at the metal. Before you touch anything, ground yourself. Touch a bare metal part of the case or use an anti-static strap. Then start with the CPU on the motherboard box, never inside the case, so you can see the alignment arrow clearly. Apply thermal paste the size of a grain of rice. More isn't better, it just spills over. Click the RAM sticks into slots A2 and B2 for dual channel. Mount the board onto the brass standoffs. This prevents the board from touching the case and creating a short. GPU goes in last because it's huge and blocks everything. Finally, those tiny front panel connectors. Power, reset, USB. The manual's diagram is your best friend. For a visual walkthrough, watch Professor Messer's 7-minute A+ hardware video. Time to test your assembly know-how. Quick question. What's the safest first step and why? Here's how this knowledge becomes a paycheck. A ticket comes in. User report screen is black after startup. Instead of guessing, you pop the side panel, see a red LED on the GPU, reseat the power cable, and the display comes alive. You document the failed component and close the ticket as hardware issue resolved. CompTIA A+ 220 11.1 Objective 3.1 explicitly covers hardware identification, and that's what employers want you to know. Spend 20 minutes a day on Professor Messer's free A+ video series. Today, watch his motherboard components clip. That one video teaches you to map every port and slot visually. Do that, and you'll walk into your first IT interview already sounding like you've been inside 100 PCs. That was a lot of hardware, so let's lock in the big 3 takeaways. 1. You can now look inside a PC and name the core components without hesitation. 2. You can explain what each one actually does. CPU thinks, RAM remembers, GPU paints, SSD stores. 3. You know data flows from storage to RAM to CPU to display, and that a bottleneck in any single link makes the whole machine feel broken. If you've got those 3, you're already ahead of most first-day IT help desk hires. Part 2 of the IT Fundamentals. Masterclass is a deep dive into CPUs, cores, threads, instructions per clock, and how to pick the right chip whether you're building a virtualization rig, a gaming beast, or a quiet home server. Hit subscribe and the bell so you don't miss it. I'll see you in part 2.